Record. All right, go ahead and ask your question.
I just had I just was wondering about number 6. On the homework, it was asking about like if there's like a bronze wire that's conducting electricity.
Yeah.
How could you tell if it's bronze? And is there like actual like evidence that would show you that it is bronze? Because I don't really.
First, you'd have to find out that bronze is made out of multiple metals, and there are different formulas for bronze. Basically, it's copper and zinc or copper and tin.
Yeah.
Actually, brass is copper and tin, and I think bronze is copper and zinc. One of the two, something like that.
Yeah.
But the way to determine if it's bronze is a number of ways. There's no one thing that would tell you it's bronze. You need multiple pieces of evidence to tell you it's bronze. One is the color. We all know what bronze looks like. It looks a lot like brass.
Yeah.
So you can't distinguish between the two that way. However, to distinguish between the two, you'd want to try and look at other characters of bronze that are easy to look at, not difficult to look at. So it conducts electricity. That's good because that means it's made out of metals, which means it could be bronze. Mm-hmm. And then the last thing you want to look at is probably, not the last thing, but another thing you might be able to look at is the density.
Yeah.
When you combine and make the metals that make bronze, the density is going to be different than either of the initial metals. Now, the density difference is going to be very slightly different. So you have to have a very good technique to be able to do that. So that's one way to do it. Another way to do it is there's something called X-ray diffraction, something like that. There's an instrument you can actually buy where you point it at the metal and it bounces off of the atoms in the metal. And
really?
Based on how it's diffracted or whatever, you can tell what the composition of the metal is. So metallurgists actually have these tools, handheld tools. They point at the metal and they can tell you the composition, and they tell you right away whether it's bronze or brass, or even tell you the source of the metal because of this certain composition in it. So the easiest way, of course, is not to buy a $5,000 instrument. It's to try and work with the density. Other than that, I don't really have anything for you as far as how you might determine if it really is bronze. But I think one more thing I could tell you is that you could look up the formula for bronze, and then you could see about separating the metals.
Okay.
Now, separating metals is really hard to do when it's an amalgam. So you probably have to do some sort of chemistry, some sort of electrical chemistry where you're doing oxidation reduction, turning one of the metals into an ion and the other one not, and then separating the two, and then take the metal that you've turned into an ion and turn it back into a metal atom and see what type of metal it is.
Right.
So it's a complicated question, and it probably takes a little bit of research to come up with a pretty good answer.
Because I did find that because it is also asked for copper, and copper is like apparently softer than bronze, but
it is. Copper is softer than bronze, and that's the reason you make bronze and brass, is because they tend to be a little harder than what you made them out of. And copper is kind of hard to come by. But copper is a soft metal, but all metals are soft. So
yeah, sure.
I think it would be a little harder, but what are you going to do for the hardness? You need a piece of copper to compare the hardness to, right? And maybe I'm overreaching on the question. Maybe the question really is not, is it bronze? Really, the question may be, is it not copper, but instead a mixture?
Yeah.
And another thing you could do, possibly, is you could melt it. Because if it were pure copper, it would melt at a particular temperature, very narrow range. And if it were bronze, it would melt over a wide range because it's impure.
Yeah. Okay. So just find like the melting point.
You could try to melt it. And, even with that, you wouldn't even have to determine the melting point. You just see if it melts over a small range, like about 3 or 4 degrees Celsius, or it melts over a wide range, like, 20 degrees Celsius.
Yeah.
When it's a mixture, some of it will melt at the lower temp of the melting temperature of the lower metal, and some will melt at the higher temp of the uh, uh, higher melting point temp metal. And so you're going to see a range.
Okay.
That was easy, but you can see that you're not going to get you're not usually going to get an answer from me. You're going to get an explanation.
Yeah. That's what I like. I like
Okay.
getting like some type of explanation for a question.
Okay. Do you have any other questions?
No, that was actually the only one I had
Okay. So are you game for doing some problems from the book?
for sure.
Okay. So let me see. So last week, I spent a lot of time going over problems in the book that were from the first half of chapter 1. So these are problems around on page 21, 22, 23. The second half of chapter 1 is more difficult because for most students, because there's a lot of math involved. And so today and the rest of this week, I'm going to focus on those problems from around page 50, 51, and so forth. Okay. So this is going to be important for the exam that is going to be in about 2 weeks, maybe 2.5 weeks. I'm going to be showing you the kind of work I expect to see on the exam. The exam is going to be over chapters 1 and chapter 2, which in previous books used to be 3 chapters. So it is pretty much a 3-chapter exam. So I'm going to do a change share screen here. And what you should be seeing now is a piece of paper with a problem on it.
Yeah, I see it.
I also use these problems to sometimes teach you things or remind you of things that you should know. Okay. All right. So the temperature of the surface of the sun is 5.5 times 10 to the third degrees Celsius. What is the temperature in Kelvin? First thing I want to teach you about this or remind you is that this is what is called scientific notation. And sometimes I write SN like a social security number, or that's actually SSN. Okay, so scientific notation is you have some number times 10 to some power. And sometimes I use the letter E for exponent. And of course, you have the unit over here. And what you need to know about this is that the number is going to be less than 10 and greater than or equal to 1. And the exponent is going to be some number that's a whole number, like -3, -2, -1, and so forth. Second thing I want to tell you is that if the exponent is greater than 0, then the number, the overall number, so I should say the scientific notation is greater than 1. So if this is a 1, this whole thing is greater than 1. If it's a 2, it's greater than 1. And if the exponent is less than 0, then the scientific notation is less than 1. So if this were 10 to the -3, this would be 0.005. Okay, and this number here tells you how many places to move the decimal over. And I don't bother with trying to remember whether or not I'm supposed to move the decimal to the right or to the left. All I do is simply take a look at that and say, hey, this makes the number bigger, so I need to move that decimal to the right because it'll be bigger. If I move it to the left, it gets smaller. So if you remember this part, that positive means bigger than 1, negative means less than 1, you'll always know which way to move the decimal. Okay, so we can move the decimal over 3 places. 1, 2, 3, and we get 5,500 degrees Celsius. The other thing you want to know about scientific notation is that you can count significant figures in scientific notation. And in this 5.5 times 10 to the 3 degrees Celsius, The number part tells you how many significant figures. And so our rules here are, since they're both non-zeros, there are two significant figures. Now, when I write it out this way, it tells us that this is precise to the hundreds, because zeros at the end are not significant unless you see a decimal. We know where the decimal is. There's no question about that. But unless we see it, those zeros are not significant. So this only has two zig figs. We'd also say it's precise to the hundreds. So I'm going to put this off to the side. And we're going to look at converting from degrees Celsius to Kelvin. So Kelvin is equal to degrees Celsius plus 273.15. Your book gives you a formula that has a whole bunch of things that you convert, but we're not going to bother with that. So we have 5,500 plus 273.15. And I'm going to actually line them up like this. In this formula, you have to know that this number 273.15 is not exact. It has 5 zig figures and it's precise to the hundredths. Okay. So I'm going to add these two up here and I get 5773.15. Now this is good to the hundreds. This is good to the hundredths. That's the precision. The more you know about a number that's given to the right, the more precise it is. So the hundreds is more precise, or the hundredths is more precise, and the hundreds is less precise. Are you okay with that?
Yeah.
Okay. When you round these numbers, you round it to the less precise position. So that means we round it to the hundreds. So we get 5800. And we drop all of these numbers, the 7, the 3, the 1, and the 5, but this 7 does make this 7 into an 8 due to rounding. And so the answer to this question would be, and this is the kind of work I would expect to see. I'd expect to see the formula. I'd expect to see this, and then I'd expect to see this. And oops, I made a mistake. I'm going to cross that 0 off. Here, make no mistake that this is Kelvin because it says Kelvin on the left. So this is the work I'd expect to see. You don't need to do all this work over here on paper, but I did it because it helped me figure out where I'm supposed to round to. In time, you're going to look at this and say, that's hundreds, that's hundredth. I round that to the hundreds, and you won't need to write this out. And maybe now's the time you don't need to write that out. Okay? So that's the rule for addition and subtraction. All right. Let's go to the next problem. Make the following temperature conversions. So here, you can see that in the first part, A, we're converting Kelvin to degrees Celsius, not the other way around. So here's the original formula that we remember. Since we want degrees Celsius, we want to rearrange this formula so it looks like this. So it looks a lot like the other formula, except it's got minus 273.15. And the steps to getting this are that, and this is not something you need to show, but this is just a quick reminder of algebra. What's your math background, by the way?
I finished my Math 50C last semester.
Well, then I don't need to show you this stuff.
Yeah.
You know how to do it.
Yeah.
Okay. So a lot of people in this class have just finished intermediate algebra, and they really need these reminders of, well, what you do to one side you have to do to the other, right? And then once you get that, you can take the C and put it on this side and put the K minus 273 on the other side, because the rule in algebra or math, it's not even an algebra rule, in math, if A equals B, then B equals A. But I call this the golden rule in algebra. What you do to one side, you have to do the other side to keep it equal. Okay, so here we're going to have 77 minus 273.15. And I always like to estimate these at the beginning, because you can see that this number is going to end up being really close to negative 200, right? So if my calculator spits out something ridiculous, I can ignore it and start again. And my issues are not meant to be exact or precise. They're meant to be within a 10%. Okay, so 77 minus 273.15. Now this one is good to the ones, and this one is good to the hundreds, so I'm going to round to the ones. So minus 196 is the temperature in degrees Celsius. So out of this is what I would expect to see on your exam for the work, what I've boxed off. Okay, with that in mind, why don't you go ahead and do B and see what you get, and then do C and see what you get, and we'll compare answers, okay?
All right.
Maybe you've already done them while I was talking, which is okay too. All right, here's what I got for B, 336K. And I rounded this to the ones because we began with 63, which is good to the ones.
Yeah.
And this one, I got 1180, and I rounded to the tens because 1450 is only good to the tens. Any questions?
Yeah. I kept mine at 1176.
That would be wrong.
Yeah.
That would be wrong. Okay, let's look at the next problem here. The average lead, new and unused, is 19 centimeters long. What is its length in millimeters and in meters? So I'm going to show you something about dimensional analysis, unit conversions, conversion factors. There are a number of different ways of calling it what it is. But I'm going to show you how to convert a number with one unit into a number with another unit of equal amount. So I've done this in other lectures, but I'm going to show you this. So here we have no doubt about this equality, that 12 inches is equal to 1 foot. I think it's so phenomenal, I'm going to write it down twice. On the left equation, I'm going to take each side and divide by 1 foot using the rule of algebra. And I get 12 inches over 1 foot is equal to 1. On this side, I'm going to divide both by 12 inches. And on this side, I get 1 is equal to 1 foot over 12 inches. And at first, you might think, well, that's weird that 12 over 1 is 1 and 1 over 12 is 1. But when we think about the units, we know that these are true, right? And here, that means 12 inches over 1 foot is equal to 1 foot over 12 inches. But that should be the case because the inverse of 1 is 1, right? So both of these are equal to 1. So you can take any equality and put one side on top, that equals 1. Put the other side on top, that equals 1. Any equality. Secondly, there's the golden rule in math, not algebra, in math. In math, the golden rule is the identity law. Anything you multiply by 1 remains the same. Anything you divide by 1 remains the same. So let me show you how we use the identity law and these guys here, which I call conversion factors, ratios, to convert 19 centimeters to meters and millimeters. So I'm going to do meters first. So to do this, we need an equality between centimeters and meters. And if you don't have knowledge that there's 100 centimeters in a meter, I can show you how to get that. So let's say that you don't have knowledge that there's 100 centimeters in a meter, because who knows, maybe this could have been nanometers and no one knows how many nanometers are in a meter, that type of thing, right? So this is how I start to get the equality, because you can't argue with that. That's a fact. But if we know that C is actually a substitution for 10 to the minus 2, so being in a calculus, you're used to this term substitution.
Yeah.
I'm substituting 10 to the minus 2 for centimeters. Now, if I multiply this side times 10 to the plus 2, then I have to multiply this side times 10 to the plus 2. And 10 to the plus 2 is 100. And 10 to the minus 2 times 10 to the plus 2 is 10 to the 0, which is 1. So here I've just proven that 100 centimeters is equal to 1 meter. So this is the way I would do it using this. Now remember, I can put either one of these on top and either one on the bottom. I'm going to put 100 centimeters on the bottom and 1 meter on the top, because that way the centimeters will cancel. Now, some people are uncomfortable with this because the 19 centimeters doesn't seem to have a numerator or a denominator. And my answer is that if you see a number that has what looks like no numerator or no denominator, it's numerator.
Mm-hmm.
Okay, so the golden rule, if I divide it by 1, I'm not changing the number.
Yeah.
So it's numerator. The other thing that's interesting is that 19 centimeters is really equal to 19 times centimeters. And that's why we're allowed to cancel these, is because when you have centimeters over centimeter, that's 1. But also, you know, if we have 19 centimeters plus 9 centimeters, that's equal to 28 centimeters, right? So
Yeah.
more proof that this is a product is that if we factor out the centimeters, and we can only do so if it's a product, we get 28 centimeters. So a number times a unit is a product. All right, so here you would get 0.019. You'd get 0.19 meters. And this is all I would expect to see out of this answer, this type of work right here. You don't need to show me all the equalities and how you got it and so forth and so on. Fair enough?
Yeah.
Now, in this particular case where you're converting from a unit with a prefix to a unit without a prefix, there's another okay way to do it. And this is it. I don't need to use a conversion factor because C is a placeholder for the real number, which is that. And then if I wanted to get rid of the 10 to the minus 2, I'd get that. And it's the same answer. So this would be fine too. Okay. It's not a trick. It's the definition of C. Now, we're supposed to also convert the length to millimeters. So we're going to go 19 centimeters to meters to millimeters. Now, the reason for this is that you may not know the relationship between centimeters and millimeters. I do, but I'm going to say that you don't know, but I'm going to pretend you know the prefixes. So we have 1 centimeter is 1 centimeter. 1 centimeter is 1 times 10 to the minus 2 meters. And for this conversion, we're going to be working with millimeters. So why don't you write that out for yourself, and then you'll compare it to what I write and see if we get the same thing, okay? Go ahead and leave it in exponential form. Do you know what a milli is?
Million?
10 to the minus 3. It's actually thousandth.
Thousandth. Okay, my bad.
So here, let's talk about the ones you need to memorize, okay?
Okay.
Mega is 10 to the 6. Kilo, like kilometer, is 10 to the 3rd. Deci, lowercase d, is 10 to the minus 1. Centi is 10 to the minus 2. Milli is 10 to the minus 3. And we call this micro, but it's the Greek letter mu.
Muse, yeah.
So it looks like to me, it looks more like a cursive U with a long tail at the front. 10 to the minus 6, you can see we skipped here. And at the top, you can see we went from 6 to 3. So now we're going to go from -6 to -9, which is nano. And I'll let you look up the actual words for these. I'm just giving you the abbreviation.
Yeah.
Pico is 10 to the minus 12. So you should know all of these. And you probably already know giga, which is 10 to the 9. Especially with computers, most computers have at least a gigabyte of memory nowadays. Okay, so now that you know that milli is 10 to the minus 3, see if you can get the analog of this using milli. So it should start off with 1 millimeter is 1 millimeter. And when you have two letters that are the same, the first one is always a prefix. The second one is a unit, and this M means length. So did you get that?
Yeah.
Okay. Now, if you don't like working with exponents like this, especially negative ones, you can take that -3 and put it on the other side as a +3. And this says there's 1,000 millimeters in a meter. I'm not bothered by exponents because I'm just so used to working with them. So here, I'm going to call this number 1, and I'm going to call this number 2, and I'm going to call this number 1 and this number 2. So I'm going to use number 1 right here. And how do I decide which side to put on the bottom, which side to put on the top? The answer is based on what I want to cancel. So I'm going to put 1 centimeter. Pardon me?
That's how I used to see it too. Just whichever one I want to cancel, I'll put that on the bottom.
That's right. So sometimes you're putting on your conversion, you're putting the thing you want to cancel on the bottom first. But if you're canceling something on the bottom over here, you're going to put the first thing in on the top.
On the top, yeah.
Yeah. So this is 1 times 10 to the minus 2 meters. And I'm going to go ahead and cancel out the CMs. And then here, how are we going to use number 2 here?
You're gonna put a 1 over 1 times 10 to the negative third. You can put that on the bottom so you can cancel out.
Right. And then, good.
On top, yeah.
And then a way of dealing with these exponents is I say to myself, if you cross the line, you change the sign. So 10 to the minus 3 becomes 10 to the positive 3 when I move it up here. 10 to the positive 3 times 10 to the minus 2, you add the numbers together. So 3 and negative 2 is plus 10, or 10 to the 1, I should say. And 10 to the 1 times 19 is 190. So this is what I'd expect to see for the solution. And we started off with 2 significant figures. We ended up with 2 significant figures. Now let's see how this plays out if we had not used these negative exponents, but instead we had done this. Do you see how this would have ended up with the same answer?
Yeah.
But probably for most people, a little easier to get to the final answer because we know 100 goes into 1,000 10 times. But either is correct. And you always want to think about your conversions, and you should always have a sense, at least for lengths, what a centimeter is, what a millimeter is, what a meter is. So if I asked you what a meter is, what would you do with your arms? No, what a meter is. How would you show me what a meter is?
I'm not too sure. Oh.
It's like a yard. Okay. So what would a decimeter be? A tenth of a meter. Yeah, more like that. What would a centimeter be? Oh, too big. I'd say it's the width of my fingernail from side to side. Maybe my pinky is more appropriate. Okay, so you could go, it's the width of my fingernail. Okay, you could be Dr. Evil for a minute.
There you go.
What about a millimeter? For a millimeter, I'd say, you know those pencils that have lead of 0.5 millimeter and 0.7 millimeter?
Yeah.
Well, 1 millimeter is a little wider than the 0.7. I try to put it in terms of what some people may be able to visualize. And so what would be a tenth of a millimeter? Well, I'd say take one of those 0.5 lead pencils and divide that into 5. That's 1.1 millimeter. You with me?
Yeah.
Now, what about a micrometer? How would a person see that? And the answer is it's too small to see with the eye. And so for a micrometer, you need a special instrument to be able to see things that are micrometer in length. And it's called a microscope. So now you know why it's called a microscope. It's for looking at things that are micrometers in length. Or maybe you already knew that. Okay. So are you okay with that conversion here?
Yeah.
Okay, let's go to the next one. So I like to throw in little nuggets of information over time that have nothing to do with the class really, but are kind of interesting. Now you know why it's called a microscope, or maybe you already knew. A compact disc has a diameter of 11.8 centimeters. What is the surface area of the disc in square centimeters? So a lot of people claim to be visual learners, but they don't bother drawing the problem. So you've learned this in math, algebra, trig, etc., calculus. Draw out the problem. So here's my compact disc, and I guess to make it really realistic, I'm going to put a little circle in the middle. Dang, you see how close that is to being like real circles?
Like actual
I'm
perfect
like,
circles.
yeah, I'm like maybe not Michelangelo, but Michael almost Angelo. Okay. Or was it Leonardo da Vinci who could draw the perfect circle?
I think it was Leonardo.
Okay.
Yeah.
So maybe I'm not Leonardo da Vinci, I'm just Leonardo. Okay, so here I'm going to draw this in. And the reason for that is I know that when I'm dealing with circles, I usually deal with the radius, not the diameter. Does that make sense?
Yeah.
Okay, so we know that an area of a circle is pi r squared. And since r is equal to d over 2, this means that the area is pi d over 2 squared, which is pi d squared over 4. Now, there's a reason I'm doing this, and I'll show you why now. Oops, my bad. I can't even copy what I've written correctly. So here we know that the radius is half the diameter. So what is half of 11.8? Well, it's 6.3, I think. No, 6.4. No, 6.9? No, that can't be right. 5.9. Okay.
You got it.
So what I'm showing you here is incorrect. It's not correct. But half of 11.8 is 5.9. And we can even ish this, right? What's 6 times 6? I know it's not 6, it's 5.9, but what's 6 times 6?
Oh, it's 36, my bad.
What's 36 times 3? A little over 100. So I'm going to say this answer should be close to 100. And let's see what we get. Now, when you select pi on your calculator, that gives you a whole lot of significant figures. And here we have 2. And so my calculator spits out 109.3588403. The centimeters is squared. In this case, oops, I wrote cubed. Well, where would I round to?
So 110.
Yeah. And that's the wrong answer. Let's see why. So over here, I have the formula pi d squared over 4, pi 11.8 centimeters squared over 4. We can estimate this answer also. 12 times 12 is 144, right? 144 divided by 4 should be around 30, and 30 times pi should be around 100. Okay, so let's see what answer we get here. 11.8 times 11.8, 139 divided by 4, and times pi. So I get 109.3588404 again. But what is my final answer here?
Oh, it's going to be 109.
109 centimeters cubed, squared, I'm sorry. So, how do I know I need 3 significant figures?
Based off the centimeters, the
Based
diameter.
based on the 11.8, because this formula is defined.
Yeah.
So that means that, and this formula is defined, so this 2 is defined, so infinite number of zig figs. And here, the mistake I made was when I halved this, I thought, oh, this is rounded to the 10th. I'm going to round that to the 10th. I could have done it this way. And the right way to do it this way would be as follows. Whoops. So we'd write 5.90 because when you take 11.8 and divide it by 2, you should get 3 significant figures. So really, for this problem, if you want to do the radius is half the diameter, the first thing you should do is this. Three zig figs, infinite zig figs, 3 zig figs. And then plug it into this formula here and go from there. Are you with me? So it's kind of nice to show you the tricky things now so that when you get to them on the test, you're reminded that, oh, I really need to be careful about significant figures. Okay, so here, the rule for significant figures for multiplication is that whichever number you begin with that has the fewest significant figures, your answer has the same amount. So any questions on that one?
No, sir.
How about square meters? So there are 2 ways we can do this. I'm going to show you a common way of doing it. We just have 109 centimeters squared, right? Now, we cannot just substitute the C. That would be wrong. Because this really means 109 centimeters times centimeters. So we'd have to substitute the C twice. So we're not going to go that route. Instead, we're going to do this. 1 centimeter is 10 to the minus 2 meters. So I'm kind of skipping a step here. And I'm going to go ahead and write 100 centimeters is equal to 1 meter. And then I'm going to show you something that is wrong. You're going to look at it, and first you might think, oh, that looks okay, but it's wrong. Let me get my hand out of the way so you can see that, what I've written. Do you see how I squared the left and I squared the right? Seems like I'm following the rules of algebra, right? But I am not, and I'll tell you why. This is like saying 100 times B is equal to 1 times A, because B and A are different, right? And then I say 100B squared is equal to 1A squared. I'm not squaring the whole side. I'm only squaring one part of the side. You're not allowed to do that. So that's why this is wrong. And if you draw a picture, so naturally this is not 1 meter by 1 meter, but I want you to pretend it is. So this is supposed to be 1 centimeter. And there's 100 of these here. And that means that here you have 100 cubes, and each of them is 1 centimeter by 1 centimeter. In other words, that little line there is 100 centimeters cubed. Or squared, I'm sorry, I'm saying cubed, it's the wrong thing. So 100 squares is what I should call that. So that's 100 centimeters squared, and that does not equal the whole 1 meter by 1 meter. So this is wrong, and you want to avoid that. So let me show you how to avoid that. It takes a little more work, but it's worth it. I want to get rid of that centimeter, and I want to use this. Which one do I put on the bottom?
Centimeter.
Does that cancel both of the centimeters?
Nope.
So what am I going to do?
You can do it again.
That's right, because I'm multiplying by 1 again. How many times can you multiply by 1 and not change the amount? Infinity. Did your dog see a cat? So this is it. And we get 0.0109 meters squared, I believe. How many significant figures in the 109? How many here? Leading zeros do not count. Tweener zeros do. So this is how you would convert that to square meters. This is the way I do it. You don't have to do it this way. I'll show you another way if you're so inclined. You can do it this way. It's the same thing. It's kind of like doing this. If I square both sides, not just a part of each side, that's okay. So I like this way better because it looks cleaner to me and I have less to think about here. Like if I did it this way, I might be apt to write 0.0109 meters instead of meters squared. Because I think, okay, yeah, great. I canceled both of those with that. And then I forget to double, square the meter. So I try to make my solutions what I call Tony proof. Because if there's someone who's going to figure out a way to screw something up, it's me. So I try to make my solutions Tony proof so I can avoid that. I'm apt to make mistakes. In fact, I think I've missed my calling in life. I should be a product tester because I will tell you how it's going to mess up in the hands of a consumer so that you can fix it beforehand. Is that a job, product tester? I wonder if you can make good money because I'm telling you, I can figure out how to how to mess stuff up. Okay, let's take a look at this one here. Some soft drinks are sold in bottles with a volume of 1.5 liters. What is this volume in milliliters, in cubic centimeters, in cubic decimeters? So for 1.5 liters to milliliters, I'm going to start with 1 milliliter is 1 milliliter. And then I'm going to start with 1 milliliter is 1 times 10 to the minus 3 liters. And then I'm going to write 1.5 liters times, which one are we going to put on the bottom?
Liter.
How many significant figures does 1.5 times 10 to the third have? 2. And how many does this have? So this is a great solution. All right, in cubic centimeters. Now with these problems, it's okay to start with something you've already done. So this is something you want to memorize, Jorge. This is the definition of a milliliter. 1 milliliter is exactly 1 centimeter cubed. So infinite zig figs and infinite zig figs. So on the first exam, to do this conversion, I would expect to see something along the lines of this. On future exams, we can just substitute. Okay, now let's convert this to cubic decimeters. And I'm going to start with centimeters cubed. Can you remember what I said a centimeter is?
The negative third.
Right, but visually.
Was it the pinky?
Yes. the
Yeah.
pinky. Now, how about 10 decimeter, a decimeter? What would that be
You want it visually or do you?
visually? Yeah, 10 of these. It's 10 of these.
Yeah.
So we know that there's 10 centimeters in 1 decimeter, right? So let's use that here to get decimeters cubed. So I'm going to let you do that and you tell me your answer and I'll tell you if you're right. Actually, I'm going to rewrite this one. You look like you're punching buttons. So this is what I have for my solution. And I know that 10 times 10 times 10 is 10 to the third. 10 to the third divided by 10 to the third is 1. So I get 1.5 decimeters cubed. And basically that's the definition of a liter. It's 1 decimeter cubed. But we don't package it in a cube. We package it in a tall bottle, right? So this is what I'd expect to see, something like it for converting to decimeters cubed. Are there other ways of doing this? Absolutely, that would be correct. And as long as you're organized and I can follow your work, you're going to get full credit. You need to have units in here. Notice there are units everywhere. Correct number of significant figures in the answer. Easy to follow. Any questions, Jorge?
No questions.
Okay, then let's go ahead and move on. An UUS dime has a mass of 2.65 grams. What is its mass in kilograms? In milligrams. So if I want to take 2.265 grams and turn that into kilograms, I need to know the relationship between kilograms and grams. And that is that 1 kilogram is 1 kilogram. So 1 kilogram is 10 to the third grams, or 1 kilogram is 1,000 grams. Now, if I asked you, what is a kilogram, so that someone might understand it, someone on the street might understand it, what would you say? This is what you,
Yeah, I
this
forgot
is
what you
what you would
said.
say. It's a little more than 2 pounds.
Okay.
454 grams is 1 pound. A kilogram is 1,000 grams. So 454 grams is 1 pound. 1,000 grams is a little more than 2 pounds. Now, what about a gram? How would you describe a gram to people? Here's the easiest way, easiest to remember. A nickel weighs 5 grams. Now, you're not telling people what a gram is exactly, but you're giving them an idea. If a nickel weighs 5 grams, if you cut it into 5 equal pieces, one of those is 1 gram. Does that make sense? So that's a really good example of a gram. I believe a dollar bill weighs a gram. Okay, so that's an idea of a gram and a kilogram. So 2.265 grams times 1 kilogram over 1,000 grams. And we get 2.265 times 10 to the minus 3 kilograms. Okay, so what's the relationship for milligram? 1 milligram is equal to 1 milligram. What's a milli again?
Was it hundreds?
Thousandth.
Thousands, my bad.
Hundredth is centimeter.
Yeah.
So there we go. So do this problem for milligrams and tell me what answer you get. Tell me when you're done and then I'll show you my answer, okay? I need some coffee. I heard it was going to rain today, but it's a beautiful day where I am. Sunny out.
It's nice here too.
Wonder how long it'll last.
I got my answer.
Great. So I put the 1 times 10 to the minus 3 grams on the bottom to cancel. And then this becomes 2.265 times 10 to the 3 milligrams. Now, I'm going to show you something that's kind of interesting. It's a trick, but it's a neat trick. This is a conversion you should not bother memorizing. 0.946 liters is equal to 1 quart. Based on what we see here, which is bigger, a liter or a quart?
Quart.
Nope, a liter's bigger.
Liter's bigger?
Yep. So here, if this is 1 liter, where would I draw my line for quart?
A little lower than.
So a liter's bigger than a quart, right? So here's the lesson I want you to learn. Smaller number goes with the bigger unit. What's bigger, 1 inch or 1 foot?
A foot.
A foot, clearly. You don't even need to look at the numbers here.
Yeah.
You can visually say a foot's longer. Which one has the smaller number?
A foot.
Smaller number goes with the bigger unit. What's a bigger unit, a kilogram or a gram?
The gram.
Nope.
Kilogram? My bad.
Kilogram is, remember,
Oh, yeah,
on
yeah,
the
yeah.
news, they always
Yeah.
talk about the police just arrested a guy with 5 kilograms of pot,
Yeah.
not 5 grams, because 5 grams, you just let them go. So kilogram is bigger. Which number is smaller? This one times nothing, or this one times 10 to the minus 3,
The 1 minus to 10 to the minus 3.
right? And these two, what's bigger, a gram or a milligram?
Would it be the gram?
The gram.
Yeah.
So which number should be bigger? The one with milligram.
Mm-hmm.
So
Okay.
these are measurements that you kind of want to get used to. What's bigger than the other? Milligram, kilogram, gram, microgram. Microgram is really, really small. You want to get used to those measurements also. What's bigger, a kilometer, a meter, a centimeter, or a millimeter, or a micrometer? You kind of want to have an idea of which one's on the big end of the scale, which one's on the small end. So when you make these conversions, you can be fairly comfortable with the numbers. Bigger number goes with the smaller unit. And that makes sense, right? If you have A times B and B times A, excuse me, A times B and C times D, if D is big and B is small, you want a big A to balance that small B and a small C to balance the big D. So, all right. So any questions about number 12?
No, I'm good.
You can see that this stuff gets kind of intensive. We're doing a lot of mental gymnastics here for quite a while. And so I know it may get tiring. If you're kind of done, I'm okay with that. But if not, let's go ahead and do this one.
Yeah, we can do one more.
Okay. A piece of silver metal has a mass of 2.365 grams. If the density of silver is 10.5 grams per centimeters cubed, what is the volume of silver? So we have to know that grams is a mass and centimeters cubed is a volume. And we want to take our 2.365 grams and turn that into a volume. So in the best of all worlds, I would be able to do something like this. So what I'm showing you is a way to do this problem without knowing the formula for density. So if I start off with 2.36, oh, that should be 5. And I want to convert this into centimeters cubed. Doesn't it stand to reason that I'd like centimeters cubed in the numerator and grams in the denominator of my conversion? And I always like to tell students this, when I use numerator and denominator, I never really clicked with which was which until I finally figured out a way that made sense to me. And here's what makes sense to me. Numerator, north. Denominator, down. If it were me, I would have called it denominator and upinator, up and down, or numerator and southinator. But here's why we probably don't want to do that, is that in the southern hemisphere, it doesn't work. Because to them, south is down, not north. All right, so if we look at this number here, 10.5 grams per centimeter cubed, 10.5 goes with the grams. What number goes with centimeters cubed when we don't write a number in a ratio like this? 1. So here's the setup. And we can estimate how many times will 10 go into 2.365? About 0.2 times, correct? Okay. How many significant figures are we allowed?
Would it be 3?
Correct. So I get 0.225. Now let me show you how we can do it another way. And that is density is defined as mass divided by volume. Therefore, volume is defined as mass divided by density. So we could have 2.365 grams over 10.5 per centimeter cubed. And we would get the same answer here. And if you take a look at the centimeter cubed on the bottom, and this might be confusing, but you might recall from algebra, you can take a fraction in the denominator, inverse it and multiply it. Or we could do this. This gram cancels that gram. 10 goes into that 0.225 times. And when I take that centimeters cubed and cross the line, it becomes centimeters to the minus cube, right? And when I cross the line again, it's centimeters cubed. So if you cross the line twice, you don't change the sign. So this would be okay also, but I wanted to show you how to do this as a pure unit analysis conversion factor problem rather than rely on a formula. Because the last thing you want is to be wondering, oh, what's the formula when all the information's right in front of you? Okay?
All right.
All right. So that's that one. And let's do one more because it's a density problem. Now this one, it might be useful to use the formula. Density is mass divided by volume. Therefore, volume is mass divided by density. And so for the water, you have 600 grams divided by 0.995 grams per centimeter cubed. And for the lead, you have 600 grams divided by 11.35 grams per centimeter cubed. Which one is going to have the larger volume? Just looking at the calculations, we can totally ish this. How many times does 0.995 go into 600? And my answer is, that's so close to 1, I'm going to call it 1. 600-ish centimeters cubed. How many times does 11.5 go into 600? Well, that's really close to 10, right? I know it's not going to be 60. If I wanted to make a better estimate, I could say like, well, maybe 55, right? Because 11.5 is a little bit bigger than 10. So this is a little less than 60. So which has a bigger volume? The water. I don't even need a calculator. And if we plug in this number, 600 divided by 11.35, we get 53. So the issue isn't bad. Now, how many zig figs are we actually allowed?
1?
1.
Yeah.
Because of the 600, for goodness sakes. So this answer really should have been 50 or 60 as an estimate. And this one is dead on for the answer. Okay. Any questions here?
No questions.
Okay. I will say with this one here, you don't really need a numerical answer because we just ask which one is bigger
Yeah.
and kind of provide an explanation. This is a perfect explanation. 600-ish is bigger than 50-ish. Duh. Okay. So I would say maybe that just as the cherry on top. Okay, Jorge, thanks for coming by.
Thanks for all the
Normally
help.
at the end of a session, I have everyone turn on their mics and say goodbye to everybody else. So say goodbye to yourself.
Goodbye to me.
Okay, and this will be posted in the module ones. It'll be posted as module 1 Q&A 01 25 21 morning.
Okay.
All right. Thanks for dropping by.
Have a good one.
You too.